So next up is Zhishao Lin from Berkeley, who is going to talk about regression-adjusted imputation estimators of the average treatment effect.
Yeah, so today I will discuss about regression-adjusted imputation estimators of the average treatment effect. So today we'll focus on the observational study. First, I will provide some general pictures of the observational study. So suppose we have some observational data and we have a lot of units, and for each unit, so suppose we have 3 characteristics to characterize the units. For specific unit I, we'll have yi1 and yi0. So we use the potential outcome framework, and yi1 is the potential outcome on the treatment. yi0 is the potential outcome on the control. We also have some observable covariates, and we use xi for these covariates. Okay, so but the previous one is the ideal case because we cannot observe the 2 potential outcomes simultaneously. What we have in reality is 2 groups of data. So we have 2 groups, the treatment group and the control group. We'll use the red ones for the treatment group and the blue ones for the control groups. So for the units from the control group, we'll observe their potential outcomes under control. And we can always observe their covariates, and also we'll observe the indicator function, indicate whether it is from a treatment group and the control group. For the units in the control group, we'll use di equal to 0 for control. And for the units in the treatment group, we'll also observe their potential outcomes on the treatment. So that's the data which we have. And our final goal is to estimate the average treatment effect, which is the expectation of the difference of the 2 potential outcomes, y1 minus y0, based on the data we observed. Okay, so a typical way to estimate, to consider this problem is to regard this problem as a missing value problem. So for example, for the unit in the treatment group, we can observe its outcome on the treatment, but for its counterfactual outcome under control, because we cannot observe it, we may imagine what will happen if this unit is given control. So we want to use the information from the control group to estimate the counterfactual outcome under control. So for the imputation method, which is we'll use the non-parametric regression to impute the missing value. So for example, for this red unit, to estimate its potential outcome on the treatment, we simply use its observed outcome because this unit is already in treatment group. But for its counterfactual outcome under control, we use a linear combination of all the outcomes from the control groups. So in the non-parametric literature, this estimator is called a linear smoother. So linear smoother can including many different kinds of matching methods in causal inference literature. So for example, for the kernel matching, it is exactly the case when we use Nadaraya-Wilson estimator to construct this non-parametric regression estimator. So for the nearest neighbor matching estimator, which is a very popular matching estimator in causal inference, it corresponds to the case that we use k nearest neighbor estimator to impute the missing value. And if we want to consider the local linear matching, it is exactly when we use local linear regression to impute the missing value. Also, we can consider maybe very complicated non-parametric regression estimator like random forest to impute the counterfactual outcome. Okay, so we will use for each unit j from the opposite group, we will use wj2i to represent the contribution of unit j to unit I when estimating the counterfactual outcome of unit I. Okay, although we have already seen that the kernel matching, different kinds of matching methods can correspond to the imputation method I just introduced. We may also want to incorporate the regression adjustment, which is I would say which is also very important because it's related to the double robust property of our final estimator. So for the regression adjustment, we'll first consider two outcome models. So the first outcome models is the expectation of the outcome given a specific covariance value as well as the treatment group. And mu0 is the expectation of the outcome given a specific covariance value as well as the control group. So to estimate these two outcome models, we can use some standard non-parametric regression methods. Because suppose we have the observational data and we already separate it into two groups, control group and treatment group. So we can simply run a non-parametric regression on each group. For the treatment group, we regress y on x. And after running this regression, the estimator will automatically estimating the this outcome model. And we can do the same way for the control group. So how can we incorporate the regression adjustment or these two estimated outcome models into our estimators? We'll follow the ways proposed by Abadi and Imbus. So for example, we consider the unit in the treatment group, and if we want to estimate its counterfactual outcome, instead of simply use yj, we'll use yj plus mu hat xi minus mu hat xj. So that's very nature because, for example, we want to know what will happen for unit I if it will be given control. But if we use xj in the opposite group, xj is not exactly the same as xi. So there will be some small difference between these two covariates. So that's why we have to use the outcome model, because by using mu xi minus mu xj, we can adjust for the covariance difference between unit j and unit I. Also, we can make adjustments for this estimator in the same way, and the final regression adjusted local matching based average treatment effect estimator is in this form, which is simply the average of the difference of the two estimated potential outcome. Okay, so there's a very important thing because we use local matching for our method because the local means that for the unit j, which is very close to unit I, will give wj to I a larger weight. But if the unit j, like this blue one and this blue one, which is very far away from unit I, then the contribution of these units to estimating unit I will be very small. So that's why we call it local, because we'll give the local ones a larger weight, but the ones far away a smaller weight. Okay, so there are some observations for this estimator. The first very important property, I would say, is that our estimator is doubly robust. We can take a look at why this estimator is doubly robust. We can rewrite our estimator in this way. And this way is very similar to the typical double robust estimator, because for the typical double robust estimator, the first one is also the regression estimator. So which is the average of the difference of the two outcome models. And the second one is the error term, but for the typical double robust estimator, the coefficients of I will be 1 over the estimated propensity score, or 1 over 1 minus the estimated propensity score. So we'll say, okay, so if we want to have the double robust property, this one will automatically estimate the propensity score. So that's what we'll show in the next few slides. So actually for the imputation method, it will intrinsically estimate the average treatment effect, intrinsically estimate the propensity score. So that's why this estimator will have double robust property. So to formally establish the double robust property, we'll need some assumptions. The first assumptions are very standard data assumptions, which including the unconfoundedness assumptions as well as the overlapping conditions. Also, we'll have some moment conditions on the error terms and outcome models, which are very nature to assume. Also, we'll have a very weak weight assumptions. So for the weight assumptions, the first part said that when we construct the imputation estimator or the non-parametric regression in the first step, we will treat each sample in the data equally. So our estimator will not depend on the index of the samples. Also, we will assume that the weight satisfies this identity. But actually, for many different kinds of linear smoothers, like an Arrow-Wilson estimator or like local linear estimator or even a local polynomial regression estimator, the summations of the weight, the summation of Wj to 1 will always exactly be 1. So this assumption will automatically be satisfied. But to allow for the maximum of generality, we may allow some decay on these summations, estimating approaching 1. Okay, so that's two assumptions for the double robust property. The first one we'll call it the density assumption, and the second one we'll call it outcome assumption. So the first one allows for the misspecification of the outcome model. So this one, mu bar can not equal to the outcome model, but we'll need these key identity holds. So this one is a summation of the weights in another form, and we'll say this one will estimate the density ratio, because this one can be written as the density ratio of the two samples problem. For the outcome assumptions, we assume the correct specification of the outcome model, but we nearly do not have assumptions on the weight. So the double robust property said that as long as either the density assumption or outcome assumption holds, then the final estimator will be consistent. So this is a very desirable property, but that's not this estimator have, and that's not the estimator only have. We'll have more stronger property. So our second observation is that the regression adjusted local matching is semi-parametrically efficient. Of course, for the semi-parametric efficiency, we'll assume stronger assumptions than the double robust property. And I will discuss about the assumptions later. So we will first take a look at why this estimator is semi-parametric efficient. So we can decompose the estimator into several terms. And we'll have some insights on why this one is semi-parametric efficient. So the first one is the average of the difference of the outcome models, the true outcome models. The second one is the error term, and the third one is a bias term. Also, we can see why, you can see from this decomposition why we need regression adjustment. Because if we do not use the regression adjustment, the decomposition will only consist of these three terms. But if we use regression adjustment, we will have additional Bn hat. So typically the Bn is not of root n order. So if we want to have root n consistency, have a central limit theorem of root n order, Bn should be corrected. So we incorporate a bias correction term, which can be incorporated by the regression adjustment. So we can see Bn hat is in a very similar form as Bn, and we'll see Bn minus Bn hat is negligible on the root n order, if we assume further assumptions. So our second step is to show that the first two terms can be used to estimate the true average treatment effect with a root n central limit theorem. So we'll see the variance consists of two parts. The first part is very standard, and the second part we can see this actually depends on the weight, which is depend on the data. So we'll say V is data dependent. But the good news is that if the following key identity is true, then V will converge in probability to a fixed number. And this number is it's very familiar because this one appears in the semi-parametric efficiency lower bound. So if the following key identity is true, which is a very important task in our paper, then under some additional smoothing conditions on the outcome models, we can indeed correct the bias. And to summarize, our estimator is semi-parametrically efficient, and the meaning of semi-parametric efficient is that the estimator is root n consistent with asymptotic variance achieves the semi-parametric efficiency lower bound. Of course, we will need some assumptions. The first four assumptions are the same as the double robust property. But to have semi-parametric efficiency, we need both density assumptions and outcome model assumptions hold. So these two assumptions must be true. This is very nature because if we have one misspecification, it is unlikely that we'll have root n consistency. Of course, it may be hold in some case, but we will not consider this case. And then we'll have further moment conditions, which are very nature. And there are two very important assumptions for the semi-parametric efficiency. So we'll call the first two parts as the outcome model smoothness, and the third part to be the density model smoothness. So the first part, the outcome model smoothness, states that the estimated outcome model can estimate the true outcome model and its derivative to some order. And of course, for the higher order derivative, the approximation accuracy can be a little bit slow. And this one, density model smoothness, is very important. It tells us why do we need local matching instead of global matching or global methods for impute the missing value. So if we use like a nearly uniform weights for all the units in the opposite group, then this term will of constant order, because there will always be a large number of units in the opposite group with a constant distance to the unit we are interested in. So if we want to have these two assumptions hold, then for the unit which is very close to x1, we will impose larger weights for this unit. But for the units far away, we'll impose smaller weights or zero weights on these units. Okay, so I will use a simple I would say a simple case to illustrate our general framework, which is the nearest neighbor matching, because K nearest neighbor is always I will say the form is much simpler than the Wilson estimator. So for the K nearest neighbor, if we choose the number of nearest neighbors to be 3, then for estimate the counterfactual outcome for this red unit I, we'll find the nearest neighbor of these red units in all the blue ones. So if we find 3 nearest neighbors, these 3 blue ones will be the nearest neighbors. Then for these 3 blue ones, the contribution of these units will be equal to 1/3, because we choose we use the K nearest neighbor estimator, and for all the other blue units, the weight for them will be 0. And our only remaining task is to estimate the density rate to show this key identity, which states that this linear combination are indeed estimating the density ratio. I will provide intuition why this is true due to time limits. So this we can consider a very first we can to the sum. Well, I will explain the meaning of this summation. So the meaning of this summation is the contribution of unit 1 to all the units in the opposite group. So we first have to find the nearest neighbor of all the blue units. Like for these blue units, we have these 3. We find these 3 nearest neighbors. These blue units find these 3 nearest neighbors. So after we finding all the nearest neighbors for the blue units, we'll see that the number of times these red units being the nearest neighbors is 3, because there are 3 blue ones finding these red units as the nearest neighbor. So the summation will be 3 times 1/3, which is equal to 1. And we can consider a very extreme case. So if there are a large number of blue units around these red units, then it will be the nearest neighbor of a large number of units, and then this one will be very large. But if there are a large number of red units, then these red units will competing with each other to be the nearest neighbor. So this term will be very small. So this summation can be regarded as a density ratio estimator, which is the density ratio of the conditional distribution for treatment and the conditional distribution for control. And the proof is related to Voronoi diagram. Okay, so we first consider nearest neighbor matching our I will say previous paper, and then we consider general framework which incorporates kernel matching, nearest neighbor matching, local linear matching, as well as the random forest. And we make a conjecture that any consistent regression-based imputation will give rise to a semi-parametrically efficient average rhythm effect estimator. Because we in this paper we prove the key identity I just introduced separately for each matching estimator. If we want to consider provide a general routine to prove this identity, it will be very difficult and is left for future work. So the talk is based on 2 papers. The first one is now accepted by Econometrica, and the second one is now under review. So that's all for today's presentation.
Excellent. Thank you very much. Thank you for